think that my cups are one of your entire recordings. So keep my things over here.
Okay. So, every time I touch this cable with my foot, something wrong happens. Not a great sign. Stay. So, not off to a great start when I forget to speak. Any questions, comments, needs, concerns, etc. from you guys today about anything at all?
Is the homework still due Monday?
Presently, yes.
Okay.
I actually took 2 questions out of it just this morning because upon further review I realized that web assignment was going to make them miserable to do. So it's actually only 8 questions now. I moved the 2 that one would take the longest and 2 involved typing in answers in a way WebAssign will never understand. So now it is only 8 questions and we have gone over all of the information you would need to do them, but today we're going to go over some specific examples that will help you with ones that we may not have done exactly like that one yet. So it's currently still due Monday at midnight. I will revise that if we get to Monday and I find it would be better to push it back, but do please be working on it. Anything else before we start today?
I just wanted to remind you that I'm coming to Friday, today's lab.
Great, thank you. Excuse me. All right. Any questions at all, even goofy ones, please ask as soon as you have them. Now today, there's going to be a couple more types of 2D vector addition questions that I want us to look at. Well, I suppose one of them will be vector addition, the other will be going back to canons for a moment, just to show you as many different types of questions with them as possible. And so after lecture today, you'll have seen cases for pretty much everything on the homework and the quiz, and you'll be set to work on it over the weekend and come with questions on Monday if you have any. And then next week, we're going to start talking about Newton's laws and forces. So, we've been primarily, when it comes to 2D motion and vector addition and drawing triangles, looking at triangles and vectors that are about displacement, which is something that is pretty physically easy to look at and draw because you just draw a line where something went, and that works nicely with the human brain because you can visualize that. But velocity is also a vector, and that means you can add it to other velocity vectors, and this is going to be a type of scenario where that is the case. The rowboat crossing a river is a common chestnut of physics example writing, excuse me. Anyone who ever writes a textbook has to include at least one of these. So let's look at one together. Again, drawing a picture is important, and how we draw it is going to depend on how we read a few things in this particular case. So, a rowboat crosses a river with a velocity of 3.3 miles per hour. All of our velocities here are in miles per hour. All of our displacements are in miles, so we don't need to worry about converting anything. I don't know why I left it in miles per hour, actually. So this is the speed of the boat. This is the speed that the boat is outputting. And we know what direction it is headed in. 62.5 degrees north of west. And this will just be, to get our scale in, north of west means you start west and then you tilt the corresponding number of degrees towards north. So this isn't going to be our exact picture, but we do know that we'll be operating in second quadrant. The river is 5.05 miles wide, and the current in that river flows eastward at 1.25 miles per hour. How far upstream is the boat when it reaches the other shore? So, let's draw an actual picture to represent this. The river is flowing east, so I'm going to draw our river running east-west horizontally across our page. Our boat, since we know that the boat is going to go west and north, I'm going to put the boat starting on the south shore. And its velocity vector, I'm going to put in a little baby coordinate system here just to help me dial in my aim, is at 62.5 degrees north of west. So we start west, we're going to tilt north, so it's a little more than halfway. It's going to look something like this. So that is our boat's velocity. And in addition, we know that the river is flowing eastward at 1.25 miles per hour. I am going to draw that vector arrow up here for reasons that, well, it doesn't especially matter where you put it because it's just the movement of the river itself. So we could put it any and everywhere within the water. I'm in the habit of drawing tip to tail, so I'm going to put it up here, and that is 1.25 miles per hour. And both of those vectors so far are velocities. We do have a third vector listed that isn't a velocity. It's actually a displacement, or a distance. And that is the width of the river, 0.505 miles. For some reason, the fact that the door always sits like half closed bugs me, so that's fixing a me problem. So, this is a pretty good sketch showing physically what is going on here. And what we are asked to find is how far upstream is the boat when it reaches the shore. Now, what that's literally asking for if you were crossing a river, say you start here, and this is the exact spot you want to end up. Your first thought would probably be get in the water and just go straight forward to where you want to go. But if the river's flowing that way, is this where you'll end up? No. You're going to move forwards and drift eastward at the same time, which is an example of the velocity vectors adding together. Your northward velocity would add with the river's velocity, and your resultant vector sum would point that way. You'd end up some distance away from where you actually intended. This rowboat sailor, this rowboatist is aware of this fact and has tilted their trajectory upstream to try to account for that. But we still don't necessarily know where they will end up on the other shore relative to where they want to end up. And that's what we're going to try to find. whichever side of this imaginary axis we end up on, you want to know how far from it we will land. Questions so far? Okay. So, what we are ultimately solving for, if we are going to keep this axis as x-axis, positive x, positive y, then we're ultimately going to be solving for delta x. So, we know river velocity, boat velocity, and trajectory, and the width of the river in the y-axis, but we want to know where we will end up in the x-axis. So, if the x-axis is what we are concerned with, my recommendation is we look at an x-axis an equation with x-axis variables in it. So, I say usually, when in doubt, just start by writing formula 3, because even if it isn't the formula you need, you've eliminated it, and then you know to write a different one instead. So, bless you. We've written a formula. Let's see if it's one that will be useful to us. We want delta x. We don't necessarily know how fast the boat is going to be moving in the x-axis specifically yet, because the boat is flowing upstream and the river is pushing it downstream at the same time. So we don't officially know VIX yet. We can find it. That is absolutely something we can look for. We just don't have that number yet. We also don't know time yet. We don't know the time it will take to cross this river, but since getting across the river is a function of the y-axis, we're probably going to need to consult the y-axis for that one. Again, something we can find, so we're listing things that we need to look for. And then we have 1/2 times ax times time squared. Now, if we assume the river's flowing at a constant velocity, and the question is implying the boat is going to consistently move at this speed pointed in this direction the entire time, would the boat be accelerating in the x-axis? No. So that's something we don't have to look for. That whole term is just going to fall away. So, the two things we need to find in order to get to delta x are VIX and time. Which one do you want to find first? Time? Is that what you said, sorry?
I said time.
Someone said time. So let's start with time. So, time, since this is the time to get across the river, and that's a function of this y-axis distance, let's look at the y-axis version of this formula instead. I seriously need to do something with these chairs. There, I did something. Delta y equals VIY times t plus 1/2 AY t squared. So, we want time out of this. We actually know what delta y is, because that's going to be our displacement in the axis that we have labeled as y. And we know the width of the river we're trying to cross. So, I'm going to label that as delta y. Whoops, the decimal point in the wrong place. So we do know delta y, convenient. We're going to need VIY, which we don't we don't have a specific number for that yet, because the boat is going to move at this velocity in this direction. That's going to have a y component, which is not necessarily this number. So VIY is something we can find but don't have quite yet. Then t, which is what we want out of this formula, plus 1/2 AYT squared. In this situation, is the boat accelerating in the y-axis? I hear a couple people muttering, which is good. I just can't actually hear you.
It is?
It actually isn't this time, because, well, it's not falling. Our y-axis isn't vertical here. We've pretty much been looking at cases where y is vertical, but the way we've drawn our system, neither x or y is actually falling downwards. We're just sailing flat across a river. And earlier we assumed the river flows at a constant rate and that this velocity and trajectory aren't changing. If it's not changing and it has a vertical leg, well, then the vertical piece doesn't change and we aren't accelerating in the y-axis this time. So even in the y-axis, that piece just goes away. No acceleration for once. That's kind of neat. So, in order to find time, we already have delta y. We're just going to need VIY, which means we're just going to have to break down our initial velocity and trajectory into its xy components. Questions so far? I'm getting a couple expressions I could read as what, which is fine. I just want to know if you guys have any issues. You're allowed to be confused. You're students, it's kind of part of your job. Okay. So, we're going to break down the boat's trajectory into an x piece and y piece. The way that I have drawn this, y is opposite and x is adjacent. So, my green markers keep dying. It makes me sad.
It's supposed to be 3.30 miles per hour.
Oh, thank you for catching that. 3.30. So from our 62.5 degree angle, if we do sine of that, y will be opposite and the 3.30 will be our hypotenuse. So sine of 62.5 will be VIY over 3.30. If we do cosine of 62.5, cosine is adjacent over hypotenuse, that will be, well, I'm just going to leave that as x for now, over 3.30. So now my calculator always worms its way into the very bottom of this thing. What do we got for y-axis?
2.93.
Very good. And how about x?
1.52.
Very good. Now, one thing to note before we move on, we are going to need this x variable in a minute. If we assume right is positive x, as we tend to, this is going to point the negative x, and since our calculators have no way of knowing that just from the numbers alone, we're going to have to put a negative there ourselves. But now we have VIY, which we can safely bring over here. Delta y is the width of the river, so 0.505 equals our VIY, which we just found to be 2.93 times time. And this will tell us a nice number for time. Oops, I almost did to the power up instead of divided. That would be wrong. What are we getting? Oh. I typed it into my own calculator incorrectly. I make mistakes. Can you repeat the answer?
0.17.
Okay. So not only did I type it into my calculator wrong, my ears didn't hear what you were saying correctly. I apologize. I'm going to add one more digit just in case. And the time unit here would actually be hours, because our delta y was in miles and the velocities we're working in are miles per hour. So we're left with hours, which would be about 10 minutes. Not a bad boat, Red. So now we have t, which we can put back over here to help us find delta x. So delta x is equal to. Now what should we put in for VIX?
-1.52.
And that would be an excellent thought. However, even if the boat is trying to do this, the river is running in the opposite direction. So the reason that I didn't label it VIX is as soon as the boat sets out, so right from the beginning of this procedure, these two run against each other, and so this is not actually the resulting speed you will move in this direction. The two vectors in the x-axis will add together, and you will actually end up moving very slowly in the negative x direction. Again, the point being, if you don't want to go that way, you want to point your boat in the opposite direction of the river flow. So what I'm going to do is, and if this notation is not how your brain works, then I will absolutely rewrite it in any way that helps. For VIX, I am going to write negative 1.52 plus 1.25, representing the two x vectors added together, the resultant slower x speed of the boat. How do you guys feel? It is okay if you don't like the way I did that. I will redo it. Anyone want me to do it a different way? Want to show some more steps and then show how we got there? Okay. I'm not reading any reactions telling me to stop, but if you want me to, if this is confusing, I want you to tell me. Adding these two numbers together, since one is negative and one is positive, is going to result in a small negative number, which again will represent the reduced speed you will move upstream because the river is flowing downstream. I always get those terms backwards. Which way is upstream? Not important. I will go ahead and solve for this number though. I think it would be negative 0.27. And then our time is still 1.73 hours. And so for delta x, that will give us a final answer of Does anyone disagree with this number? Please tell me if you do, because I'm apparently in the habit of writing down numbers wrong. Wait.
What's up?
Yes, I literally just wrote the number down wrong.
Oh.
Again, if something is confusing, if I do anything that doesn't make sense, please call me out on it.
I didn't even notice.
Okay, now that is a small number, but it's also in units of miles. So we want it to be small. I don't want to walk a whole mile at least, not after just crossing a river. I didn't walk up the coast of the river. And this will represent the distance. If the boat lands, well, the boat will end up landing. This is not a scale drawing at all. The boat will end up landing here, approximately, not to scale. Questions? Okay. I've already been talking for a little bit, and I'm thirsty. So let's take a quick break before we look at one more quick example and then run out of here for a weekend. That's not right. It doesn't really matter, but I will definitely see the cap and pick up the wrong marker because of it.
Yes, you do. Okay, I do, but just like talk about it. But I don't want to do all that. Like, I don't want to do all the hike. Like, I like to hike, but not every day. But Italy? But what if I do tornadoes? Where are they going in Italy?
Any questions, needs, concerns, etc.
Here.
Before we continue?
I don't know.
Okay, we got one more quick example I want us to look at because there is a case of this on the homework, and I don't want the differences in it to throw you. We're going to do one more cannon problem, but this one is simplified in that we already know how long the projectile is in the air because it's a firework that'll go off in 5 seconds. And we're ultimately, our job is simply to figure out where it's going to go boom. So I'm going to hold this up. So just to read the question in full. Considering launch conditions below, what will be the X and Y location of the firework when it goes off? The conditions we're told is the firework is going to be launched at a velocity of 100 meters per second, pointing at 75 degrees and upward from the x-axis. It's going to begin on a cliff 15 meters above the ground, and it will go off 5 seconds after being launched. We are told to start our coordinate system for our answers in terms of the base of the cliff. So what we're solving for is X final and Y final in terms of the spot we have labeled 0, 0. We are told time in the air, which is nice. Means we don't have to go do a quadratic to find it this time. And we are also told where we begin. And the firework, is going to start right there. So its initial X position is 0. And its initial Y position is 15 meters in the air. I'm labeling things slightly differently because where the firework starts is not necessarily our origin in this case, and I'll show you how labeling initial and final separately from each other will be useful in a minute. Now, we're going to need to divide this up into its pieces so that we can manipulate its the X and Y at launch velocities separately. So we will employ a small amount of trig. So sine is opposite over hypotenuse. Sine of 75 will be VIY over 100. Cosine is adjacent over hypotenuse, so cosine of 75 will be VIX over 100. Oops. I am getting 96.6 meters per second Y and 25.9 meters per second X. Does anyone disagree with those? Okay, so that's two more variables that we know to start with, which is convenient. VIX, VIY, And I suppose this might not be entirely accurate for a firework, but assuming it is a projectile, what will its x and y accelerations be as it moves through the air? Assuming it is a projectile, that it was launched and that it doesn't have a rocket strapped to it.
Acceleration will be 0.
Very good. And in the y?
Negative 9.8.
Thank you. I did hear someone say gravity. Thank you very much. Okay. I will probably relabel this question because I suppose most fireworks actually do have rockets and therefore they would be flying. So we'll assume this is more of the type that is slung rather than the type that has a rocket on it. So we want x final and y final. And with projectile motion, a great place to start is always Formula 3. So we'll look at each axis separately. X-axis, we want x final. So I'm going to split delta x into x final minus x initial, because delta anything is always final minus initial. But we know that the initial x position is 0. It starts directly above our origin, so this whole term is just going to become 0. Equals our VIX, 25.9. times our time in the air of 5 seconds, plus 1/2 times 0 times 5 squared. So this whole term falls away. We just have one piece of multiplication to do. Does anyone disagree with 129.5? All right. Excuse me. Now for the y-axis. We want y final, so I'm going to separate delta y into y final minus y initial. The reason I'm separating them is because where we start, well, we're not defining our endpoint in terms of our starting point now. We're defining our endpoint in terms of some other point. So if we wanted to know where it went relative to where it started, we could simply solve for delta y like we've been in the habit of doing. But setting our origin at a different spot means that delta y alone is not what we want. We want to know the coordinate of where it ends up. So we've split delta y into those coordinates to set them apart from one another. Any questions about this specific quirk?
Where does the 20 come from?
The 20 came from my head, making things up again. Thank you for catching that. We start 15 meters above the floor. Oops, sorry. Thank you. Any other questions? How many times have I just written the wrong thing today? At least twice. All right, filling in the rest. VIY is 96.6 times time is 5 plus 1/2 negative 9.8 times 5 squared. We know everything but YF, so we can solve accordingly. I'll actually write out a few more lines to show the simplification. When I do 96.6 times 5, I get positive 483. 1/2 times negative 9.8 times 5 squared is going to give me negative 1. Yep, there I go again, writing the wrong thing. 122.5, and we're going to need to bring the 15 over from the other side. We're going to add positive 15 to both sides. And those are the three terms we're going to add together. Does anyone disagree with those three terms? Did I write anything down wrong again? Okay, so last step, we add three numbers together. And I then, please tell me if you disagree, get a y final coordinate of 375.5 meters above the floor of the canyon. Any disagreements? Any issues getting to that number? All right. And so our final coordinate answer is going to be 129.5, comma, 375.5 end parentheses. And that is exactly the spot where boom will occur. And this sort of thing is very useful if you are, again, putting on a municipal fireworks show, but you want to make sure that the explosion doesn't happen within the tree line. Any questions? Yes?
When you write the Y and the X after the final, why do you have the mark above it?
Oh, this? This is a habit that I developed predominantly from my physics majors classes. It's a way of indicating, again, that this is just in the X direction. I suppose it's already marked over here, but I tend to overlabel I try to overlabel instead of underlabeling. So it is just a unitless, numberless way to further indicate that. Oh, and yeah, it just means X direction. It doesn't have a number associated with it. Anything else? All right. Go enjoy your weekend. Do be working on your homework so that you can come prepared with questions on Monday. And have a wonderful day and weekend and lunch, I hope.